Digital summing can be accomplished by adding together two or more signals. When it comes to writing our computer code, this is another place where we're going to use element-wise indexing to go sample by sample through our signals. Then, it's just a matter of using basic addition to add together the corresponding samples. As an example, let's say we have two signals. What we're going to do is start at time sample 1 and add together the amplitude values for both of our signals. We'll store the result in our output signal at time sample 1. Then we'll move on to time sample 2 and add together the amplitude values of our signal there. Store the result in the output signal also at time sample 2. We'll repeat this process all the way through the end of our signals. The one thing we have to be careful of in MATLAB is when we use array addition, we're required that the arrays, or our signals in this case, have the same length. If one of the signals is shorter than the other one thing we can do is add zeros either to the end or to the beginning of the signal, such that they're the same length. We just have to decide how we want the signals to line up with each other. Otherwise, it's nothing more than just basic addition. So let's go ahead and look at writing some computer code to add together two signals. Here I'll demonstrate the process of digital summing, which is performed by adding two signals together using element-wise addition. I'll begin with the basic example here in the command window. Let's say we have two arrays. These will eventually be our signals. The first array has a name of A. It has the values 3, 4, and 5. Can create this array, and then we'll have B, which has the values 6, 7, and 8. And what we like to do is add these together, or when it comes to signals, this will be mixing or blending them together. This is where we can use the addition operator with arrays. When I execute this command, the way that this works is MATLAB will index and go element by element through and combine the appropriate terms. So here we start at element 1. We do 3 plus 6 in the resulting array. The first element has the value of 9. Then we move on to the second element. 4 plus 7 equals 11. And move on to the last one. 5 plus 8 equals 13. This is what we'll now do with audio signals. So we'll start out our script by clearing off the command window and clearing out the variables. Now let's say we're going to combine together two test signals. It'll be pure tones at 440 Hz and 880 Hz. Let's put in some initial parameters. This will be things like our sampling rate of 48,000 Hz, which means we have a sampling period, 1 over our sampling rate. We'll say that our time vector now for our signal starts at 0, goes up by our sampling period, and it's 1 second long. Let's also transpose t so that it's a column vector instead of a row vector. Now let's declare the frequencies of test signals. We're going to have two separate frequencies here. Let's call the first one F1. That's going to be 440 Hz. F2 is going to be 880 Hz. Now we'll synthesize signals. We're going to have two separate ones. Call the first one signal 1. This will be a sine wave. It's going to have 2 pi times F1 times t. Now, because we're going to be combining two of these signals together, what I'm going to do is scale the amplitude so that's only 0.5 or decrease it by about 6 decibels. Now we'll have a second one, also 0.5 multiplied by sine wave 2 times pi times F2 in this case times t. Now what we can do is listen to signal 1, and then we'll also plot them after I listen to signal 2. Now this time through, let's listen to the 880 Hz. Now we'll go ahead and plot them. Signal 1 and t by signal 2. Keep in mind, the way that we're plotting them now, they're going to be separate. We haven't yet blended them together. So I'll run the script. We'll see our figure window. What we need to do now is zoom in so we can look at the waveforms. All right, so we should be able to see a couple cycles of the signals. Our blue signal is 440 Hertz, and our orange signal is 880 Hertz. The orange one goes through 2 cycles for every 1 cycle of our blue one. But what we're visualizing here is 2 separate signals. Let's now go through the process of adding them together. We could use array addition like I showed you before, and we could have something here called output of signal 1 plus signal 2, and that would work just fine. For the sake of using our control structures, I'm also going to advise and suggest that we try out using a loop. This is again explicitly element-wise addition. So we're going to go through each sample in these signals. Start at 1. We'll go up through the length of signal 1. Put the statement here end to complete the loop. Now we're going to index our output signal. It's going to be based on signal 1 plus signal 2, indexing a different sample each time through the loop. Now when we're done, let's go ahead and listen to the output signal and then also plot the output signal. Run the script. Now let's zoom in to look at the result. Here we can see that our signal is no longer a pure tone. In fact, we have a complex waveform. It has multiple frequencies that have been added together. So this is the process of adding to arrays. There's one more thing that I want to show you that you have to be careful of when you're performing this process. We are required that the signals have the same length, the same number of elements when we're going through this loop. So as an example to show you the problem, if I go back to the command window, start out with this basic example. A was equal to 3, 4, 5. And B was equal to 6, 7, 8. Well, if A has another element that I add in here, make this a value of 1. So now A has 4 elements where B only has 3 elements. If I try and add A plus B, we end up with an error that says matrix dimensions must agree. So the way that we can get around this so that we add these things appropriately is that we can go back to the array that has the fewer number of elements. If we put in zeros here so that now they have the correct number of dimensions. So this way when we add them together, A plus B, we get the correct result. You get 3 plus 6 is 9, 4 plus 7 equals 11, 5 plus 8 is 13, 1 plus 0 is 1. So any number plus 0 is going to return that same number. So we can use this to ensure that our arrays are the correct size. Now if you wanted to, you could put the 0 on the front end of the array, but it would shift B over so that it lines up differently with A. So keep that in mind. It's up to you to decide how you want these signals to line up. So let's go back to our example we were looking at before with an audio signal. So now let's create 2 separate time vectors so that one signal goes for 1 second and the other signal goes for 2 seconds. We'll say, in fact, that T1 here is going to go for 2 seconds. We'll use T1 when we're synthesizing signal 1. And we'll have a separate one for signal 2. Except in this case, we're not going to have it go as long. Now we have signals that have a different length. Okay, put in here T2. Now the issue that's going to come up is as we start to go through this loop, we want to index based on the signal that has the longer length. But we're going to get to a point where we're indexing samples in signal 2 that don't exist. So when we run the script, we'll see that we receive an error. It says index exceeds matrix dimensions. In other words, we are indexing part of signal 2 an element that doesn't even exist. So we are receiving an error. What we can do is come up here and put zeros in. This is called zero padding the array. So say signal 2, we're going to use array concatenation, where we add some zeros onto the end. We need to add in specifically the number of zeros that are missing so that it adds up to the correct length, which is going to be, in this case, 48,000. Now we put the square bracket on the end, and this is how we can concatenate zeros onto the end of our signal. The last thing we need to do is go down here to our plot and make it T1 instead of T, because we changed that variable up above. Now we can run the script, visualize the output, and listen to the resulting output signal. Let's zoom in and see that here at the first half of the signal, we have a complex waveform composed of 2 separate tones. But then when we get to the second part of our signal, after time second 1, we've just dropped down and we have our original 440 hertz signal while we are adding a bunch of zeros to it. So this is the process of adding 2 signals together while also taking into account when we perform this element-wise addition, we need the arrays or the signals to be the same length.